Hi, welcome to this lecture on mathematical methods for biologists. So far we have been studying about derivatives and how to use calculus in different contexts, and today we will so far we studied different formulas and how to use those to compute and to calculate derivatives. Today we will discuss, see if we have data. If you do an experiment, what we will have is a data set. We will have a table. You will have an x column and a y column. You have 2 or 3 or many columns. Given this, how can we calculate derivatives? So the title for today's lecture is Numerical Calculation of Derivatives. If you have data, how to compute derivatives? That is a question that we will answer. If we have data from an experiment, how do we compute derivatives from that data? That is a question that we will address today. So to do that, let us start with think about what we have. So what is known here is you have some function f of x, and we said that this derivative is df by dx. So typically this derivative we wrote m. Sometimes people also write this f prime. F prime, this means df by dx. So one prime symbol here means one derivative, which is same as m. We call it m, which is the slope. So this is the way we would compute this, and the way we did to do this given a curve was the following. That is, we had any curve f of x. So we had some curve x versus f of x, and the way we did was that we took any 2 points and found out the corresponding the function value, and we said that this minus this divided by this minus this, that is, we said delta y or delta f here by delta x. So this is our delta x and this is the delta f or delta y. So this distance minus the divided by this distance, and if you do this for a small enough delta x, you will get nice perfect answer to derivatives. So this is what we did so far to compute derivatives. Now what we have is data. So let us think about what do we get if we have data. So let us say what we have is a curve from a data set. So we have, instead of this curve, what we have is data given to us. So these are some data points. We don't have this full curve, we only have this data. So for 0 it is 0, for this there is a value, for this there is a value, so this is what we have. For each point, this is the data that we get experimentally. So experimentally what we have is essentially a table. X, which is this axis, and whatever we measure in the y axis could be concentration, it could be whatever, so some f. And then we have data points 0, 0, 1, 1.3, 2, 3.2, 3, 5.6, some data like this. So this is what we have 0, 1, 2, 3, 4, 5. So for each value correspondingly we have some y value. So this is 4, 0, 0. For 2, for 1, let us write this as 1.3. For 2, let us write this as 3.2. For 3, let us write this as 5.6, and so on and so forth. This is, for example, I am writing this. Now if you want to calculate the derivative, the slope at any point here, let us this slope if you want to calculate, If these values are close enough, we can accurately calculate the slope, which is this difference divided by this difference. So 5.6 minus 3.2 divided by 3 minus 2. So this would give us the data, this would give us the slope for this particular. So each point, each segment, we can calculate slope. So this is the way to numerically calculate the slope. If you think about it, if you want to generalize this, what we will have from an experiment is some table which is x and f of x. What we have, we will have x1, x2, x3, x4, x5 and so on and so forth. Correspondingly, for x1 there is some f corresponding to x1, there is some f corresponding to x2, there is some f corresponding to x3, there is an f corresponding to x4, there is an f corresponding to x5. Right? This is what a typical graph would look like. So typical experimental data, if you just draw this red data, this is, let us say, this is the first point, this is our x1, this is f corresponding to x1. Let me call it f1 for simplicity. This is x2 and there is some f corresponding to x2, and similarly there is x3 and there is an f corresponding to x3. So for corresponding to every point for x, there is a corresponding y value, that is the value that we are measuring, then this is what you would have. So given this is the slope here, so we can calculate the slope here. So let me write on this side the slope. So for these two together, for these two data together, given x1 and x2 together, so similar things let me write again. So what are we having? We are having x1 corresponding to f1, f of x1 if you want, x2 corresponding to f2, x3, f3, x4, f4 and so on and so forth. So then I can calculate the derivative here. So given these two data, x1, x2, f1, f2, I can write f2 minus f1 divided by x2 minus x1 is the slope between these 2 points. So if I were to plot this as a graph, and if I have these 2 points and I can calculate the slope, this divided by this. Similarly, I can calculate the slope between these two. Slope corresponding to this, I can write f3 minus f2 divided by x3 minus x2. This is the slope between the next 2 points. If you have this point and this point, the slope between this is this. And similarly, I can find the slope between f3 and f4. So I can find 3 slope values corresponding to this for here. So f4 minus f3 divided by x4 minus x3. So given 4 data points, I get 3 slope values. Let me call this m1, this is m2 and this is m3. So I can get 3 slope values corresponding to 4 data points that I have. If I have 4 data points like this, x1, f1, these are 2 values that I would get from experiment. So I have 4 data points. From these 4 data points, I can calculate 3 slope values. Any 2 you take in the neighboring ones, you can calculate a slope. So as we know, the first derivative is basically the difference. So the standard formula of the first derivative, as we know, it is also called the forward difference formula. If you know f function at x plus delta x and function at x, the f plus x plus delta f of x plus delta x minus f of x divided by x plus delta x minus x is the f prime of x. This symbol here is prime. So f prime of x is the first derivative, and this will give you approximately the first derivative. This is the numerical way of calculating this. But if you look at it here, if you look at this, I could actually calculate the derivative taking these two or these two. So as far as this point x2 is concerned, if you want to calculate the point at x, derivative near x2, I could either use f2 and f1 or f2 and f3. What am I trying to say? What I am trying to say is the following, that if you want to calculate derivative at a particular point, so let us say you have this graph and you want to calculate derivative, then we have function and the corresponding x and y values you have. If I want to calculate the derivative near this point, I can either calculate derivative using this data, that is x1, x2, x3, x4. So I can use, there is f1, f2, f3, f4. I can use f3 or x3 or this. So one of it is called a forward difference. If I use x and x plus delta x, if I take this and this, that is called a forward difference formula. So that's why here f of x plus delta x minus f of x by x plus delta x minus x. So this is, so if we consistently use always the forward, this is the most popular one, I would say, where we consistently take the higher one and the lower one, the f of x plus delta x minus f of x divided by delta x. You could also take the backward one, that is, I could just write, so what I want, the slope at near 2, right, near x2, the slope near x2, I could write, as I said, f3 minus f2 divided by x3 minus x2, or you could also write f2 minus f1 divided by x2 minus x1. If we consistently calculate everywhere, if let us say if we were to use this, then this the next one, this is the next one. Consistently if we use, we would get the similar answer everywhere. So either use this or use this consistently. So the other formula is called the backward difference formula, which is f of x minus f of x minus delta x divided by x minus delta x. So this is also we could use. So this is also a formula. If you want to calculate the derivative at x, either you could take f of x and subtract f of x minus delta x, the previous point, and find the difference, or you could take the next point and subtract the value from the next point f of x plus delta x and minus f of x and calculate this difference. So this is another way. But there might be a situation where you have a lot of data points. Imagine that you have a lot of data points very close by. So let us say you have a lot of data points very close by, and you want to calculate the derivative at this particular point. So you want to calculate derivative for this particular point x. It is also fine to calculate this slope, that is, take this point and take this point, and this slope can be also said to be the slope at x. This is an equivalent way of saying all of these are correct. These are, depending on what way you want, you could use any of this formula. So there is also called a there is a forward difference formula, there is a backward difference formula, there is also a central difference formula, which is using these 2 points, right. So this is this point, I could call it x plus delta x, this is x minus delta x. So if I use these 2 points and the corresponding f values, the formula would look like this: f at x plus delta x minus f at x minus delta x divided by 2 delta x. So this is, you take 2 points, which is 1 point slightly above this or next to it, and 1 point slightly below this or just behind it, and find those difference, and that would be also a valid, interesting formula for, or right formula for computing the derivative, first derivative. So here f prime of x. So remember, this prime means derivative. F prime of x is equal to f at x plus delta x minus f at x divided by 2 delta x. Another way of thinking about this is the following: that imagine that you have this data. So we had these data points here, 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 here. Now let us take these 2 points. Correspondingly we have, now let us call this, so let me call this x1, this is x2, this is x3. Correspondingly you have here f1, f2, f3, and of course f4 and f4 here. Now if we calculate the slope here, that is, if I calculate the slope here, which is f3 minus f2 divided by x3 minus x2, this is a slope. But this is a slope corresponding to what x value? So one could claim that this is a slope. I took these 2 and I took this. So I could say that this is this slope m, but m is for what x value? I could say that this m is for this x value. So if I take this x value, which is between x2 and x3, right? If I take this x value corresponding to some number between x2 and x3. So let us write here 0, 1, 2, 3, 4, and correspondingly we have. So this, if I just take value 2 and 3 and use this formula, I could say that this m is a slope at 2.5 when x at x equal to 2.5, in between value. So you could say that by doing this, I got the slope at 2.5. This is the equivalent way of saying at some x value in between x2 and x3. So this is another way of saying it. Once we consistently do this, any of this would give us correct answer. This central difference formula is very interesting because it could be really useful and it could be more accurate in some cases a little bit, but so let us calculate, think about it once more. So you have this value 0 here, 0 here. Then let us say corresponding to this, let us write down some values. So let us say their values are 0, 1, 2, 3 and 4, and here correspondingly you had 1.5 and 4.2 and 8.9 and 15. Let us say these are the corresponding y values that I got, or the f values I got. Now, if I calculate the slope between 2 and 3, so I could take this delta x and I could take this. So if I do this, I could write this slope as 8.9 minus 4.2 divided by 3 minus 2. So this would give us some value. This is a slope corresponding to, I could say this is a slope, so this slope is corresponding to 2.5. Now what I could get, so for this data 1, 2, 3, 4, 5, so imagine that I have this data which is corresponding to 1, 2, 3, 4, 5, and you have correspondingly, so let us say 0, so they have 0, 1.5, 4.2, 8.9, 15, 26 or some values like this. You could calculate the corresponding slope between these two values. So you could take these two values and write the slope between this. So 1 minus 0 divided by 1.5 minus 0. So you could write the slope here and say that the slope is between 0 and 5. So slope at 0.5. So I could take another table here. I could make another table here which is x versus m or f prime equivalently f prime. So here you have 0 and 1. So between 0 and 1 I could take 0.5 and find the slope which is this minus this. So this I could write the slope. Then I could write 1.5 and 1.5 is between 1 and 2. So I could write 4.2 minus 1.5 divided by 2 minus 1. Right? So I could write 4.5 minus 1.5, 2 minus 1 is 1. Here I could write 1.5. So this is correspondingly here 1.5 minus 0. Similarly, I can calculate the slope at 2.5. The slope at 2.5 is 8.9 minus 4.2 divided by 3 minus 2. So 8.9 minus 4.2 divided by 3 minus 2. So the point I am trying to make is that the central difference formula, we could calculate slope by central difference formula and say that this corresponds to the slope which is at a value between those two x values that we took. So we take, if you want to calculate the slope at x, we could take the value at x plus dx, take the function at x plus dx, take the function at x minus dx, find the difference divided by 2 times delta x. So this is what is numerically done here. So you have 1, 2, 3, 4, 5, 6. So correspondingly you have x square which is 1, 4, 9, 16, 25, 36. And these are the data points. You have x and x square, and we have the f prime of x which is this difference 4 minus 1 divided by 2 minus 1 and so on. And so this is computed using forward difference methods. So look at this, how this is computed. This is computed using forward difference method, and we could get corresponding derivative formula. Now the question is, we have this first derivative, how do we compute the second derivative? So we need to also compute the second derivative. So let us think about this quickly. So what we have is x1, f of x1, x2, f of x2, x3, f of x3, x4, f of x4 and so on and so forth. From these two I can calculate m1, from these two I can calculate m2, from these three I can calculate m3. So I have 3 derivatives, and correspondingly I will have an x value. So I could take it x1 or x1 between this value, but consistently if you want to calculate second derivative, you could also calculate c1, which is the second derivative. So consider these two as your functions. So as you know, the second derivative c is dm by dx. This is what second derivative is. So take these two values and corresponding x values, right? So you could take m2, so you could write c1 as m2 minus m1 divided by the corresponding x values for this, right? Delta x for this. So if you do this properly, m2 itself, remember m2 itself has a delta x. m2 is f of x plus delta x minus f of x divided by delta x. So you have another delta x here. Similarly, between these two I can calculate c2. So given 4 data points, I have 3 first derivatives and 2 second derivatives, c1 and c2. So these two values I can take and calculate c1. These two values I can calculate and calculate the difference between these two, which will be a derivative of m, and that will be corresponding to the second derivative. So if you write this, just remember m itself can be written as f of x plus delta x minus f of x divided by delta x, and there is a divided by delta x again here. So if I do this, I will get a delta x square. So the numerically second derivative can be written as f of x plus delta x minus 2 times f of x plus f of x minus delta x by delta x square. So if I do this, if I known the values of f at different points, so what is it known to me? I have what is known to me is just this f values. If I just know this f values, so let us say I know this x1, x2, x3, x4, x5 and so on and so forth, and corresponding I have f1, f2, f3, f4, f5. This formula says that use f at x plus delta x. So if I just wanted to calculate, any 3 points you take, you can calculate a second derivative. So let us take these 3 points. I can calculate the second derivative between these 3 points, and the second derivative formula, if you look at here, this is f at x plus delta x minus 2 times f of x minus f at x minus delta x. So you have to know f of x, you have to know f at x plus delta x, you have to know f at x minus delta x. So these 3 things you have to know. So here the assumption is that the x1 minus x2, all these delta x's are same. If you assume all of this delta x are same, what you could do, you could write this as f4 minus 2f3 plus f2 divided by delta x square, delta x square, which is the difference between delta x is x3 minus x4 or x3 minus x2 minus x1 or so on. Sorry, x square, delta x square. So this would give you c, the second derivative corresponding to this value, let us say c, corresponding to the value x3. So corresponding to this value x3, if you want to calculate second derivative, take a point above this, take a point below this, and use this formula here that would give us the second derivative. So this is f double prime of x. So double prime means 2 derivatives, second derivatives, which is also we wrote as c of x. So this is the way to calculate second derivatives numerically. Given these 3 data points, we can calculate second derivatives. Here if you take any 3 data points, we can calculate second derivatives. So finally, to summarize, I could write this in a different way. I could write slope at location I at f at I plus 1 minus f at I divided by xi plus 1 minus xi. This is another way of writing general formula for slope. Similarly, for curvature second derivative, which is ci, we could write this formula, which is f at ci is f at I plus 1 minus 2 fi minus plus f I minus 1 divided by 2 xi plus 1 minus there is no 2 here, xi plus 1 minus xi whole square. Assuming that all xi and xi plus 1 are same, for the difference between all x values, if you take it as same, we would assume this as the formula for the second derivative. So I urge you to read a little bit more and learn about computing first derivative and second derivative. Given a data set, we can compute first derivative and second derivative using this formula. With this, we will stop this lecture where we computed first derivative and second derivatives numerically. See you in the next class.